Hi, my name's Toby, and today I'd like to talk about what we mean by mean. And by mean, I mean average, as in adding up a bunch of numbers and then dividing by their count. This is a common thing to do, but I often hear that averages are useless or even misleading. But I think this simple operation is actually almost always meaningful and is sometimes the best way to describe a system's behavior. In this talk, I'll try to explain why I think that in many cases we should be looking at average latency. I'll go into a little bit of the history of why tail latency has become so important, and then I'll explain some of the math behind how to think about averages and the kinds of behavior they describe. Finally, I'll describe an example service based on real-world data and show how the effects we care about are described only by average latency and not by anything in the tail. Now, I think many of us will default to using the average to reduce a group of measurements to a single value. And if it's not always the correct thing to do, it's usually pretty good. But there's a number of people who will push back on talking about the average value for really a wide range of data, but especially in the context of computer systems for latency. It's pretty easy to go online and find a lot of people being derisive about average latency. Like, a lot of people. They call it cringe or suspicious or useless and wrong or, well, I think this guy might be a little bit lost, but even those well-versed in statistics will say it has little value. It's almost become a shibboleth for those in the know. So it kind of feels like pretty much everyone has decided that average latency is bad, that you're wrong to use it, you shouldn't look at it, don't even measure it, because at best you're fooling yourself, and at worst you're lying to your users, which, ouch. Except for Mark. Shout out to Mark. You're a real one, wherever you are. So where does this come from? First, I want to look at how average latency got this reputation, and I think it comes down to two main things, which I'll call the Amazon reason and the Google reason, for the sake of an easy way to refer to them. I'll call them this because some really basic Ethernet research brought me to these two sources. The one on the left is from a Twitter thread where Andrew talks about how a group of engineers realized that what was driving customers away from the site was any web page that took longer than about 6 seconds to load. And as a result of that, they put their focus into cutting down the loading times of the longest pages. The article on the right is about a famous Google paper where Dean and Barroso talk about the effect that tail latency has on Google's internal systems. Both of these are very good, and you should check them out. So what I'm calling the Amazon reason really boils down to what people are willing to put up with. Humans have a lot going on, and we're easily distracted. If we feel like something's wasting our time or taking too long, we'll easily pivot to another activity. If you're scrolling through TikTok, for example, and a video takes over a second to load, well, that's time enough to realize that it's 2:30 in the morning and you really need to get some sleep. But if it only takes 500 milliseconds, well, while that's still noticeable, by the time it registers, the video's already playing, and then she's chopping wood with a claymore, and that's all you want. That's all anybody wants. The Google reason is a little bit more technical, and has to do with the way that Google handles some user queries. Specifically, what Google does is hand a request off to many, many subprocesses, each of which complete their fraction of the task in parallel. This is a pattern called fanout, and what it does is it makes the parent task take as long as the longest subprocess. Because of math I don't have time to get into, latencies that are rare for each subprocess can easily become common for the parent process under this pattern. So given both of these, it absolutely makes sense that the fraction of a percent of the longest running RPCs will dominate your application's performance. And I think this is why it is so common today for people to react with aversion to the very idea of measuring something as far away from the tail as the mean. So given these very good reasons for caring about the high quantiles of a latency distribution, why would we ever care about the average? Well, the answer has to do with what the mean is and the unique properties it has, as well as some of the assumptions baked into the Amazon and Google reasons that might not apply to your service. These aren't assumptions of scale, but rather of application. In this section, I'm going to explore what an average really is and how best to think about it. I'll get somewhat mathematical, but there are no formulae or equations. In a real mathematical sense, the mean is the center of mass of a probability function. This doesn't mean that values will be clustered around or even close to the mean. In this picture, very little stone is directly above the fulcrum. Instead, there's a large pile close to it, but out to the left, while there's a very small amount of mass way up on the right. Samples from a distribution can act the same way. Individual samples can fall far from the mean, but once you get enough of them, it's the point they all pivot around. Now, the word enough is doing a lot of heavy lifting there. You can't just assume that if you get a large value above the mean, then a small value will be next. This is called the gambler's fallacy, and it's wrong. Instead, the relationship between mean and enough is governed by the law of large numbers. This is a mathematical theorem that describes how far the average of a number of samples will fall from the true mean. This graph is an illustration of the law of large numbers. The x-axis plots the number of samples drawn from 1 to 1 million. Notice that it's logarithmic. The y-axis plots the distance from the sample averages to the distribution's mean. This means that even highly skewed distributions will eventually get smoothed out with enough samples, as values very far from the mean are balanced by values on the other side that are either just as far or more numerous. This is a latency distribution from a production Dropbox service, and it was used to produce the values on the previous slide. It has been rescaled so that the mean of the distribution is exactly 100 milliseconds. You'll notice that it looks very little like a bell curve, with this huge tail swinging way out to the right. For a long time, I had trouble understanding why bell curves were given so much space in discussions about probability, when none of the distributions in my day job looked at all like them. But this was because I didn't realize how much the systems around me were subject to another theorem, called the central limit theorem. The central limit theorem describes what happens when you add up a bunch of random numbers. There are some constraints, but the gist is that the more random numbers you add, the more the result will look like a bell curve. This slide shows the result of adding different numbers of samples, from 1 to 128. By the time we're adding even 16 samples, we're pretty much bang on. But, and this is the critical part, this is part of my thesis statement, so I'm going to get big. Bell curves are completely described by two numbers, the mean and the variance, which is another way of saying standard distribution. The percentiles of the underlying distribution that gave rise to the bell curve are completely irrelevant. Distributions with longer tails will have greater variance, but this changes only the size and not the shape of the bell curve. But, okay, what does that matter? When do we add up a bunch of random numbers? Well, it depends on what we're building. Google's fanout isn't this, certainly. Fanout is equivalent to drawing a bunch of random numbers from a latency distribution and then picking the largest one. This is an operation described by a branch of probability called order statistics. But there are other different operations, which I'll bet good money your service does, that can mathematically be described as adding up a bunch of random numbers. The reason this is important is that if we care about the wrong properties of our dependencies, we'll build poorly. This is a doorway framed in new construction. Most of the wood you see is dimensional lumber. This horizontal piece here is called a header, and these vertical pieces are called jack studs. The header bears the weight of the floor above and transfers it around the opening to the jack studs, which transfer it to the wall below. The size of the header and the number of studs required is a function of the width of the opening. Jack studs are made of 2x4 lumber and are being compressed along the long axis. So what we care about when we put weight on them is how much compression they can take in that direction. Studs tend to fail by buckling, but we can prevent that by adding more. The header, meanwhile, takes load along the short axis. This deflects the header downwards, putting the top part of the header in compression and the bottom part under tension. If the header is too narrow, it will fracture. So for headers, we don't care about compression strength, but flexural strength. If we tried to build a door by maximizing the flexural strength of the jack studs and compressional strength of the headers, the house would collapse. So if we're building a system that needs to provide a certain level of service, it's important to select dependencies in a way that can help us with that. The Amazon model from earlier was very human-centric, but a lot of our systems involve robots talking to other robots. Robots don't have the same attention span issues that humans do. They're not going to get bored and open Twitter. That's why we give them the menial work. For example, a photography website might generate thumbnails in many different resolutions based on user images. These kinds of jobs don't have the hard latency requirements that user interactive traffic does, but that doesn't mean there are no latency requirements. You don't want these thumbnails being delayed by hours. Instead, we often think about how long it would take to finish processing a batch of thumbnails, a batch job. Now we can reconceptualize how we think about the work. The robot isn't encoding one thumbnail quickly, it's encoding thousands of thumbnails, possibly in parallel, but certainly not all at once. But this is just adding numbers from the same latency distribution over and over, which is exactly what the central limit theorem describes. So if the Amazon model, with its impatient users, and the Google model, with fan-out, describe services that are sensitive to the tail latencies of the dependencies they're built on, then we should also be aware of a third model, a kind of batch model, that's comprised of many sequential requests and does not have the character that any single request, if it takes too long, will break the whole thing. And when you start looking for it, you'll see this all over the place. Another place for it is any sort of buffer or queue, especially one where traffic is converted from human-centric to robot-centric. For example, a disk system that offers extremely low write latency by offering a cache of solid-state disk. Once user writes are stored on SSD, they can be copied into slower, second-tier storage in a way that doesn't affect the user. But the latency requirements on this copy are not secondary. In fact, they are critical. If the SSDs fill up, the system either can no longer accept writes or must pass writes directly through into slow storage. So there must be a minimum throughput from SSD to the second tier. This action, of copying writes out of SSD and into the second tier, has all the characteristics of the situation we are describing. And in fact, there is a famous law, Little's law, that says that in the steady state, the size of a queue is given only by the average arrival rate of new work and the average processing time of work. If we are building any of these systems, the quantity in our dependencies that we need to care about the most in terms of performance is average latency. Also, just very quickly, this picture was the result of a stock image search for Little's law, and I couldn't not, all the others were bad. So I want to close out with an example of a service that has these properties, and show you how changing the tail latency of a dependency doesn't really affect the performance at all, but improving the mean of the dependency, even if it makes the tail worse, improves our service's performance. Let's say you have a service that stores sensitive data. You promise your customers that if they delete data, it will be gone within 24 hours. For compliance purposes, you are required to check every object you store and verify that it should exist. If it doesn't, you must delete it. Objects cannot go unverified for more than 48 hours. Your SLI for this is the maximum of all the times since each object has been verified. Your SLO for this service is that the SLI will be under 24 hours. Your SLA is that if this goes above 36 hours, you start crediting customers. This is the same latency histogram as earlier. We'll pretend that this histogram represents the latency of checking a single object. Here I've marked the mean, the median, and the 99th percentile of our dependency service. The mean, as promised, is 100 milliseconds, while the median is much closer to the first largest mode. The 99th percentile is way over to the right at 450 milliseconds. If we were monitoring the latency of our dependency, this might be what it would look like. The data is simulated from the histogram on the previous slide. Here, we are pretending that our dependency is receiving 12 queries per second, which is the amount of traffic necessary to run through 1 million entities in 24 hours. We aggregate polling periods into 30 seconds and plot the 99th percentile, the mean, and the median here as a time series graph. So the question is, given this latency profile, how long would it actually take to make 1 million sequential queries to this service? Well, the central limit theorem says the answer would be normally distributed around 1 million times 100 milliseconds, with a standard deviation of the square root of 1 million times the standard deviation of the original latency distribution. This is the calculated time to finish all 1 million objects, if they are processed sequentially, in hours. Note first that this is above our SLO of 24 hours. Note second how small the range of values are. Even though the latency of the service we depend on is quite variable, that doesn't really translate at the same scale to the output of the total job. eyeballing the graph, virtually all of the runs finish in the same 12-minute span. I don't mean to imply that if you look at averages, all your jobs will finish on schedule. In real life, the underlying distribution would not be static and would itself change over the course of a day. Rather, I want to draw your attention to the fact that the features of the underlying dependency that shape our service's SLIs are its mean and its variance, and not the tail. Now, consider a modification to our service that results in this new latency distribution. The first mode is largely unchanged. Perhaps it's served from a cache, while the second mode has been bunched much more closely around 250 milliseconds. Note how the mean is never numerically close to any of the values from this distribution. The effect is striking in our graphs. The P99 has improved by almost 40% at the cost of only 10% higher mean latency. Of course, you might hesitate to accept such a change based on the context in which you are seeing this graph. I encourage you to be honest with yourself about whether you would notice the degradation in mean latency if you saw it. It's not really visible in this graph. And whether you are graphing it at all. If this change happened to your service, you might only notice the P99 latency improvement. And as we can see, the P99 in our service is degraded by about 3 hours. Imagine how frustrating this would be. Such a fantastic improvement in the P99 of the dependency service, and yet it makes our service worse. What would happen if we decided to reduce the mean latency at the cost of increasing P99 latency? Like the previous example, this latency distribution keeps the median and all the requests below it the same, at 45 milliseconds, but pushes request latencies above it away from 325 milliseconds, so that the tail is all smeared out. Now the P99 latency doesn't even fit on the chart. Take a moment to imagine what you would do if you noticed a dependency with these graphs half an hour after deployment. The P99 latency has gone haywire. It's up 35% and much spikier. If you bothered to look at the mean latency, would you notice the difference at this scale? It's down 20%. That's not much in absolute terms, 20 milliseconds compared to the P99's 165 milliseconds. But what effect does it have on our SLI? In fact, this was the change necessary to bring our service within SLO. Even though requests below the 50th percentile did not change at all, optimizing the mean latency slightly had a profound effect on our service. In this talk, I've gone over the nature of the mean and described the ways in which it can affect our services. When we're building a system, it's important to know what we're building it out of and how the properties of those things can help or hinder us. I hope I've convinced you that there are some systems that depend more on the average latency of their dependencies than on the tails. Finally, for some light homework, I want you to look up Little's Law on Wikipedia and try to use it to calculate the size of some queue in your own service and see how relevant the average really is. Thank you.